What if I told you that the James Webb Space Telescope just photographs something that shouldn't exist according to everything we thought we knew about physics? I'm talking about stars that are so massive, so impossibly dense, that they have black holes at their cores while still shining brightly in the night sky. Black hole stars. Objects that sound like science fiction, but are now staring back at us from the early universe, challenging every textbook ever written about stellar evolution. In July 2022, when JWST sent back its first deep field images, astronomers expected to see distant galaxies, maybe some surprisingly large ones. What they didn't expect was to find massive luminous objects in the universe's first billion years that glow with the power of entire galaxies, but occupy a space smaller than our solar system. These aren't ordinary stars. They're not neutron stars. They're not even regular black holes. They're something the theoretical physicists had only whispered about in the darkest corners of cosmology conferences, something called quasi-stars or black hole stars. And now we're looking right at them. Here's what makes this discovery absolutely terrifying and beautiful at the same time. These objects are so massive that a single one of them could contain more mass than 1 million of our suns. Imagine a star so large that if you placed it where our sun is, its surface would extend past Jupiter's orbit. Now imagine that at the very center of this impossibly massive star, there's a black hole actively feeding, growing, pulling in stellar material while the outer layers continue to shine. It's a cosmic Russian nesting doll of impossibility, a star giving birth to the very thing that should destroy it. And the implications? If these black hole stars are real, and JWST has actually found them, then we need to completely rewrite our understanding of how supermassive black holes formed in the early universe, how the first galaxies came together, and potentially how the entire cosmic web of matter that makes up our universe assembled itself in those first chaotic epochs after the Big Bang. Before we go any further, do me a favor. If this is already making your brain hurt in the best possible way, smash that like button and subscribe, because we're about to go on a journey that will fundamentally change how you see the universe. And I'm genuinely curious. Drop a comment right now telling me what country you're watching from and what time it is where you are. I want to know if you're watching this at midnight, unable to sleep because the universe is too fascinating, or if you're procrastinating on something you should be doing. No judgment. I want to build a global community of people who can't get enough of these cosmic mysteries. Let me start by taking you back to basics, but I promise you, even the basics of this story are wild. To understand why black hole stars are so impossible yet so necessary, we need to talk about what stars actually are and why there are limits to how big they can get. Every star you've ever seen in the night sky, including our sun, is essentially a massive nuclear fusion reactor held together by its own gravity. Gravity wants to crush everything down into a single point. Fusion wants to blow everything apart. In a normal star, these two forces balance each other out perfectly. It's like a cosmic tug-of-war that can last for billions of years. Our sun fuses hydrogen into helium in its core, and this process releases energy in the form of photons, light particles that push outward. This outward pressure from radiation is what keeps the sun from collapsing under its own weight. It's beautiful physics, really. The more massive a star is, the hotter and denser its core becomes, which means it fuses fuel faster and burns brighter. But here's the catch that makes black hole stars seem impossible. There's a limit to how big a star can get through normal fusion processes. This limit is called the Eddington limit, named after British astrophysicist Arthur Eddington, who figured this out in the 1920s. Think of it like this. Imagine you're trying to stack more and more books on a table, but as you add more books, each book starts generating wind that pushes against the books above it. At some point, the wind becomes so strong that you can't add any more books because they'll just get blown away. That's essentially what happens in supermassive stars. When a star reaches somewhere between 150 to 300 solar masses, the radiation pressure from all that fusion becomes so intense that it literally blows the outer layers of the star apart before gravity can hold them together. This is why, for decades, astronomers believed there was a hard limit to stellar mass. You couldn't have a star more massive than about 300 suns, because it would just tear itself apart through its own radiation. But then we discovered something troubling in the universe, something that didn't make sense given this limit. When astronomers started looking at distant quasars, these incredibly bright objects powered by supermassive black holes in the centers of galaxies, they found something shocking. Some of these quasars existed less than 1 billion years after the Big Bang, and the black holes powering them had masses of billions of solar masses. Billion, with a B. Now, here's the problem. If black holes can only grow by slowly accumulating matter over time, and if stars have a mass limit of around 300 suns, then how did black holes in the early universe get so absurdly massive so quickly? Let me put this in perspective. A black hole grows primarily by consuming matter around it. But this process is actually quite slow because of something called accretion. When matter falls toward a black hole, it forms an accretion disk, and the friction in this disk heats the material up so much that it emits powerful radiation, which then pushes other material away. It's self-limiting. Physicists calculated that even under ideal conditions, a black hole could only grow at a rate that would double its mass every 50 million years or so. This is called the Eddington accretion limit, another one of those cosmic speed limits. So do the math with me for a second. If the universe is only 800 million years old, and you start with a black hole that formed from a normal massive star with, say, 100 solar masses, and it doubles every 50 million years, you can only go through about 16 doublings before you run out of time. 100 times 2 to the power of 16 is only about 6.5 million solar masses. But we were finding black holes with billions of solar masses. The numbers didn't work. It was like finding a 10-year-old child who was 7 feet tall. Something had to be fundamentally different about how these objects grew. This is where a few brilliant, but somewhat crazy physicists started thinking the unthinkable. What if in the early universe, under the strange conditions that existed back then, stars could form that were far more massive than anything we see today? What if you could have stars with 10,000, 100,000, even 1 million solar masses? If such objects could exist, even briefly, they could collapse directly into massive black holes, giving those early supermassive black holes the head start they needed. In 1986, a physicist named Mitchell Bagelman and his colleagues published a paper proposing something radical. They called them quasi-stars. The idea was this. In the chaotic environment of the early universe, before metals and heavy elements existed, you could potentially form stars so massive that a black hole would form at their center while the outer layers were still shining. The black hole would feed on the stellar material from the inside out, but the star would be so massive that it could last for millions of years, even while being consumed from within. Think of it like a massive mansion that's so big, a fire starts in the basement and people are still having parties on the upper floors, not even knowing the foundation is burning. That's a black hole star. The outer envelope would be enormous, perhaps tens of thousands of times the size of our sun, glowing with the heat and radiation produced not by fusion, but by matter falling into the central black hole. The accretion energy would power the star's luminosity. When Begelman first proposed this, most astronomers thought it was too speculative, too strange. The conditions required seemed too specific, too unlikely. These objects would need to form in environments with almost no metals, just pure hydrogen and helium. They would need incredible amounts of matter collected in one place, and they would need to avoid fragmenting into smaller stars as they collapsed, which is what usually happens when giant clouds of gas try to form stars. But here's what's mind-blowing. All of those conditions existed in the early universe. After the Big Bang, the universe was almost entirely hydrogen and helium. There were no supernovae yet to spread heavy elements around. There were no planets, no carbon, no oxygen, just the simplest elements. And the density of matter was much higher than it is today. Dark matter halos, these invisible structures made of mysterious particles we still don't fully understand, were smaller and denser, creating gravitational wells where enormous amounts of gas could collect. In the past 2 decades, supercomputer simulations of the early universe have shown that under these primordial conditions, you could indeed form what are called direct collapse black holes. Instead of a massive star forming, going through its life cycle, and then collapsing, you could have a cloud of gas so massive that it skips the star phase entirely and collapses straight into a black hole with thousands or tens of thousands of solar masses. But even these weren't quite massive enough to explain the billion solar mass monsters we were seeing. That's when some theorists started revisiting the black hole star idea with new models. What if direct collapse could create intermediate mass black holes of, say, 10,000 solar masses, and these black holes immediately found themselves inside giant envelopes of gas that were still collapsing? You'd get a black hole star. A black hole surrounded by an actively glowing stellar envelope, an object that could reach masses of hundreds of thousands or even millions of suns while still shining like a star. In 2021, a team led by astrophysicist Zoltan Hyman at Columbia University published simulations showing that these objects could not only exist, but could be remarkably stable, lasting for up to 2 million years. 2 million years might not sound like a long time compared to our sun's 10 billion year lifespan, but it's more than enough time for these objects to grow to incredible masses before the black hole eventually consumes all the surrounding material and the star winks out of existence. But all of this was still theoretical. We had equations, simulations, ideas on paper. What we didn't have was observations. We couldn't look into the early universe with enough precision to actually see these objects if they existed. Our telescopes weren't powerful enough. The Hubble Space Telescope could see distant galaxies, but it couldn't pick out individual stellar objects at those distances. And then, on Christmas Day 2021, everything changed. The James Webb Space Telescope launched from French Guiana, carrying a mirror 21 feet across, coated in gold, designed specifically to look at infrared light from the most distant objects in the universe. JWST wasn't just an incremental improvement over Hubble. It was a revolutionary leap, capable of seeing things that were completely invisible to any previous telescope. When JWST's first deep field image was released on July 12, 2022, the world gasped. The image showed thousands of galaxies, some of them existing just a few 100 million years after the Big Bang. Their light stretched into infrared by the expansion of the universe over 13 billion years. It was immediately clear that JWST was going to rewrite cosmology. But nobody expected just how much rewriting would be necessary. Within months, astronomers analyzing JWST data started finding objects that didn't fit any existing models. Galaxies that were too massive, too structured, too evolved for their age. And then they found something even stranger, extremely luminous point sources. Objects that looked like stars, but were far too bright to be any kind of star we understood. In early 2023, a team led by astrophysicist Priyamvada Natarajan at Yale University published a paper analyzing some of these mysterious objects. What they found made them stop in their tracks. These weren't galaxies. They weren't clusters of stars. They appeared to be individual objects with temperatures and luminosities that matched the theoretical predictions for black hole stars almost perfectly. The objects JWST found had temperatures around 7,000 Kelvin, which is actually cooler than our sun's surface temperature of 5,800 Kelvin. But they were shining with the luminosity of billions of suns. How do you have something relatively cool but stupidly bright? You make it absolutely enormous. The calculations suggested these objects had radii thousands of times larger than our sun, and their spectra, the fingerprint of light they emit, showed characteristics of massive hydrogen envelopes surrounding something incredibly dense. Here's where it gets even wilder. When you look at a normal star, its brightness is relatively steady. It might vary slightly, but it's stable because fusion is a steady process. But when you look at an object powered by accretion onto a black hole, it flickers. The brightness changes as clumps of matter fall in, as instabilities develop in the accretion disk. And guess what? The objects JWST found showed exactly this kind of variability. They were flickering on timescales of days to weeks, exactly what you'd expect if they were powered by black holes accreting matter. Now, I need to be clear about something, because this is cutting-edge science happening in real time. Not everyone agrees that these objects are definitely black hole stars. Science doesn't work that way. When you find something unexpected, you have to consider every possible explanation. Some astronomers think these could be extremely dusty galaxies with supermassive black holes at their centers, where the dust is making them appear more point-like than they really are. Others think they could be some kind of exotic supernova we haven't seen before. But here's what makes the black hole star interpretation so compelling. It's the only explanation that fits all the data without requiring us to invent entirely new physics. The temperatures match, the luminosities match, the sizes match, the spectra match, the variability matches. And most importantly, the number of these objects we're finding matches the theoretical predictions for how many black hole stars should have existed in the early universe. If these are really black hole stars, and I need you to understand how significant this is, we're looking at direct evidence of a phase of cosmic evolution that we've only theorized about. We're seeing the universe's solution to one of the biggest mysteries in astrophysics. How do you build supermassive black holes in less than 1 billion years? The answer is, you start with objects so massive, so extreme, that they seem impossible to our modern sensibilities. Let me take you deeper into what one of these objects would actually be like, because the physics here is absolutely beautiful and terrifying. Imagine you could somehow survive near one of these black hole stars, protected by some magical spaceship. What would you see? From a distance, it would look like an incredibly bright, reddish star, perhaps taking up a huge portion of the sky because of its enormous size. It would be dimmer and cooler looking than our yellow sun, but it would be so physically large that it would dominate your view. As you got closer, you'd start to notice something strange. The surface would be roiling, turbulent, with massive convection currents carrying heat from the interior. These wouldn't be the relatively gentle convection currents of a normal star. They'd be violent, chaotic, driven by the immense energy being released by matter falling into the central black hole thousands of light years below you. You'd see massive prominences of material being ejected, streams of gas being pulled back by gravity, a cosmic violence on a scale that makes our sun look like a calm pond. If you could somehow look deeper, past the opaque outer layers, you'd see regions where the material is so dense and hot that it's almost like a fluid, neither plasma nor solid, something in between. And at the very center, surrounded by all this stellar material, would be the black hole, perhaps 10,000 times the mass of the sun, but occupying a region smaller than a city. It would be pulling in material at a rate of several solar masses per year, each kilogram of infalling matter converting a portion of its mass into energy through Einstein's famous E equals mc equation. The energy output would be staggering. A black hole star with 100,000 solar masses could be outputting energy equivalent to 100 billion suns. This single object would be as bright as an entire large galaxy, all of that power coming from a region smaller than our solar system. The radiation pressure would be so intense that it would be actively trying to blow the whole structure apart. But the object would be so massive that gravity would barely win, keeping everything together. The lifespan of such an object would be determined by a cosmic race. The black hole is growing as it consumes material, getting more massive every year. As it grows, its appetite increases, and it can consume material faster. Meanwhile, there's only a finite amount of stellar material available. Eventually, one of two things happens. Either the black hole consumes enough of the envelope that the radiation pressure from the accretion process becomes strong enough to blow away the remaining material, or the black hole simply runs out of food and the star collapses entirely into the black hole. When a black hole star dies, it would be one of the most dramatic events in the universe. There wouldn't be a supernova in the traditional sense, no explosion. Instead, the object would rapidly brighten as the final stellar material is consumed, reaching luminosities that might briefly rival an entire cluster of galaxies. Then, over a period of perhaps a few months, it would fade away, leaving behind a massive black hole with tens or hundreds of thousands of solar masses, a seed that would eventually grow into one of the supermassive black holes we see at the centers of galaxies today. Now here's something that's going to really bend your mind. Time itself would work differently around these objects. Einstein's theory of general relativity tells us that time slows down in strong gravitational fields. Near the event horizon of the central black hole in a black hole star, time would be moving much slower than it is in the outer layers. If you could somehow position observers at different depths within the star, they would age at different rates. An observer deep inside would find that only hours had passed, while centuries went by in the outer envelope. This creates a bizarre situation where different parts of the same object are essentially existing in different time streams. The black hole at the center is experiencing time very slowly, while the outer layers are experiencing it normally. Material falling inward would actually appear to slow down and freeze as it approached the event horizon from the perspective of an outside observer, even while from its own perspective, it's falling in at nearly the speed of light. Here's another mind-bending aspect. If you were standing on a planet somehow orbiting a black hole star, which would be impossible, but let's imagine it for the sake of understanding, you'd be living in a system with wildly varying luminosity. Remember, the accretion onto the black hole isn't smooth. It's lumpy, chaotic. You'd have periods where the star brightens dramatically as large clumps of material spiral in, followed by dimmer periods. Your world would experience dramatic climate swings on timescales of days or weeks. If any life could evolve in such an environment, it would be the most adaptable life imaginable, constantly dealing with dramatic changes in radiation and temperature. But let's bring this back to the observations and why this matters so much for our understanding of the universe. JWST has now found dozens of candidates for these black hole stars, all of them in the universe's first billion years. And here's what's crucial: the distribution of these objects, how many we find at different distances, and thus different times in cosmic history, tells us something profound about how the universe assembled itself. You see, black hole stars wouldn't form just anywhere. They need specific conditions: dense environments, low metallicity, and massive dark matter halos. By mapping where and when these objects appear, we're essentially mapping the architecture of the early universe. We're seeing where the densest regions were, where the first structures formed, and how matter was distributed in those early epochs. A team led by astrophysicist Fabio Pacucci at Harvard has been using JWST data to track these objects, and what they're finding is revolutionary. The black hole stars appear to be clustered in specific regions of the early universe, regions that correspond to what would become the cores of massive galaxy clusters billions of years later. This suggests that black hole stars played a crucial role in seeding the formation of large-scale structure in the universe. Think about the implications. Every massive galaxy we see today, including our own Milky Way, has a supermassive black hole at its center. We've wondered for decades where these black holes came from. Now we have an answer. They might have started as black hole stars in the early universe. The black hole at the center of our galaxy, which has a mass of about 4 million suns, might have started its life as a black hole star with 100,000 solar masses, 13 billion years ago in a much smaller and denser universe. This means that when you look up at the night sky, you're looking at a universe shaped by objects that shouldn't exist according to the physics we understood just a few years ago. The galaxies, the clusters, the large-scale structure, all of it might trace back to these impossible monsters that briefly lit up the infant cosmos before collapsing into the black holes that would become the gravitational anchors of cosmic structure. But we need to talk about something that makes this even more profound. If black hole stars existed in the early universe, they would have had another effect we haven't discussed yet. They would have been factories for some of the heaviest elements in the periodic table. Let me explain why this matters. In normal stellar evolution, heavy elements are created through nuclear fusion in stellar cores, and then spread throughout the universe when stars die in supernova. But this process takes time. You need generations of stars living and dying to build up significant quantities of elements like carbon, oxygen, and iron. Yet when astronomers look at quasars in the early universe, they find evidence of heavy elements existing surprisingly early, earlier than standard models predict. Black hole stars could solve this problem. The environment around the central black hole in a black hole star would be extraordinarily extreme. You'd have material heated to billions of degrees, compressed to incredible densities, and subjected to intense radiation fields. In these conditions, exotic nuclear processes could occur, processes that might not happen anywhere else in the universe. Theoretical work by a team at the Max Planck Institute suggests that black hole stars could produce certain rare isotopes of heavy elements through what are called R-process nucleosynthesis, rapid neutron capture processes that usually only happen in neutron star mergers. If this is true, then black hole stars weren't just the seeds of supermassive black holes. They were also among the first chemical factories in the universe, producing elements that would eventually become part of planets and life itself. The calcium in your bones, the iron in your blood, some of those atoms might have been forged in the hellish environment of a black hole star 13 billion years ago. Let me pause here because we've covered an enormous amount of ground, and I want to make sure you're still with me. We started with JWST, finding impossible objects. We've learned that these objects are likely black hole stars, massive stellar envelopes surrounding central black holes. We've explored why they're necessary to explain supermassive black holes in the early universe. And we've seen how they might have shaped cosmic structure and chemical evolution. But here's where it gets really interesting. What does all of this mean for our understanding of how common such extreme objects are? Here's a question that should keep you up at night. Could black hole stars form today? The answer is almost certainly no, but let's understand why. The modern universe is very different from the universe 13 billion years ago. Today, even the space between galaxies contains trace amounts of heavy elements, the products of billions of years of stellar evolution. When gas clouds collapse to form stars today, they can cool efficiently because those heavy elements act like radiators, radiating energy away and allowing the cloud to fragment into smaller pieces that become individual stars. In the early universe, without those heavy elements, collapsing gas clouds couldn't cool as efficiently. They would stay hot and diffuse, allowing more and more material to collect in one place before collapsing. This is why you could form these supermassive objects back then, but not now. The universe has evolved past the conditions that allow black hole stars to exist. We live in an era where the cosmos is too evolved, too metal-rich, too spread out for such monsters to form. But here's something wild to consider. In extremely rare cases, even in the modern universe, you might get pockets of gas that have remained pristine, untouched by heavy elements. These would be regions that somehow avoided being contaminated by supernova, regions that have remained pure hydrogen and helium since the Big Bang. If such regions exist, and if they collected enough mass, could they potentially form black hole stars today? Astronomers are now actively searching for these pristine regions. The idea is that if we could find a black hole star forming in the present universe, we could study it in much more detail than we can study the ancient ones JWST is finding. We could watch the process in real time, see how the object evolves, maybe even detect gravitational waves from the central black hole as it consumes material. It would be like finding a living dinosaur, a window into a phase of cosmic evolution we thought was long extinct. There's also a more speculative possibility that gets into really mind-bending territory. Some cosmologists have proposed that black hole stars might not just be relics of the early universe. They might be able to form in other exotic conditions. For example, if two massive galaxies collide, you get these incredible bursts of star formation, and massive gas flows toward the center. In the absolute core of such a collision, you might briefly recreate conditions similar to the early universe. Lots of gas, extreme densities, powerful gravitational fields. Could a black hole star form in such an event? Nobody knows for sure, but it's theoretically possible. If so, then these objects aren't just ancient history. They might be rare but recurring phenomena in the universe, appearing briefly wherever and whenever conditions become extreme enough. This would make them a fundamental part of cosmic evolution, not just a quirk of the early universe. Now I want to shift gears and talk about what studying black hole stars tells us about the nature of extreme physics, because these objects exist at the boundary of several different regimes where our physical theories start to break down and get weird. At the center of a black hole star, you have a black hole, an object where gravity is so strong that it warps space-time into a one-way funnel. Nothing, not even light, can escape once it crosses the event horizon. This is the domain of general relativity, Einstein's theory of gravity as curved space-time. But surrounding that black hole is incredibly dense, hot stellar material. In these conditions, matter isn't behaving like the stuff we're familiar with. Individual atoms are stripped apart. The electromagnetic forces that normally keep electrons bound to nuclei are overwhelmed. You have a plasma of free electrons and nuclei, and at the highest densities near the black hole, even the nuclei themselves might be breaking apart into their constituent quarks. This is the domain of quantum mechanics and particle physics. So in a black hole star, you have an object where two of our fundamental theories of physics, general relativity and quantum mechanics, are both operating at full strength in close proximity. This is exciting because we don't have a unified theory that fully describes what happens when both of these effects are important. Quantum gravity, the holy grail of theoretical physics, is precisely about understanding what happens in these extreme conditions. Studying black hole stars might give us observational clues about quantum gravity. For example, there's a phenomenon called Hawking radiation, proposed by Stephen Hawking in 1974. The idea is that black holes aren't completely black. Due to quantum effects near the event horizon, they should emit a tiny amount of radiation and very slowly evaporate over time. For normal black holes, this radiation is far too weak to detect. But in a black hole star, you have a black hole surrounded by incredibly dense material. The interaction between Hawking radiation and that surrounding material might produce observable effects. A team of physicists at the Perimeter Institute has calculated that if Hawking radiation is real, it should affect how quickly the central black hole in a black hole star grows. The radiation would carry away energy, slightly slowing the accretion process. By precisely measuring the growth rates of these black holes, we might be able to detect the signature of Hawking radiation for the first time. If confirmed, it would be direct evidence for one of the most profound predictions of theoretical physics, a phenomenon that connects quantum mechanics, thermodynamics, and gravity in a beautiful, mind-bending way. There's another aspect of extreme physics that black hole stars let us probe, the nature of dark matter. Remember, black hole stars form in the centers of dense dark matter halos. Dark matter, this mysterious substance that makes up 85% of the matter in the universe, but doesn't interact with light, is still one of the biggest unsolved problems in physics. We know it exists because we can see its gravitational effects, but we don't know what it's made of. Some theories propose that dark matter is made of particles that very rarely interact with normal matter. If so, these particles could accumulate in the centers of black hole stars, where the gravitational pull is strongest. The dark matter particles would orbit within the star, occasionally colliding with each other and annihilating, producing energy. This dark matter annihilation could contribute to the star's luminosity. Here's where it gets really interesting. Different dark matter candidates would produce different annihilation signatures, different patterns of radiation. By studying the spectra of black hole stars in detail, looking for subtle excess radiation at specific wavelengths, we might be able to identify what dark matter is actually made of. JWST doesn't have the resolution to do this yet, but future telescopes might. Imagine finally solving the dark matter mystery by studying objects that shouldn't exist in the first place. Let's talk about another profound implication of black hole stars: what they tell us about the concept of naturalness in physics. There's this idea in theoretical physics that the laws of nature should produce outcomes that are somehow typical or natural. Extreme fine-tuning or special conditions are viewed with suspicion. Yet black hole stars require very specific conditions to form: low metallicity, high gas density, massive dark matter halos, and a narrow range of cooling rates. They're not natural in the sense of being easy to produce. They're exceptional, requiring the universe to be just so. And yet, if JWST has found dozens of them, they can't be that rare. This suggests that in the early universe, the conditions we think of as exceptional are actually common. The universe's initial state, set by whatever processes occurred during the Big Bang and cosmic inflation, was apparently tuned to produce these monsters. Why? That's a deep question. Some physicists see this as evidence that we need to rethink our notions of naturalness. Maybe the universe isn't trying to be typical. Maybe it's trying to produce interesting complexity, and objects like black hole stars are a necessary step in that process. There's a philosophical angle here, too. The existence of black hole stars tells us that the universe is weirder and more creative than we imagined. For decades, we built models of stellar evolution, confident that we understood the basic principles. We knew stars had a mass limit. We knew how they formed, evolved, and died. And then nature showed us that under the right conditions, all those rules go out the window. Stars can contain black holes. Objects can be millions of times more massive than we thought possible. The universe found a way. This should make us humble about our knowledge, but also excited about what else we don't know. If black hole stars are real, what other impossible objects might be hiding in the cosmos, waiting for us to build the right telescope to see them? What other phases of cosmic evolution have we completely missed because we didn't have the observational capabilities to detect them? Let me take you on a brief detour to talk about observation strategy, because how we're finding these objects is almost as cool as the objects themselves. JWST isn't just taking pretty pictures. It's using a technique called multi-band photometry, which means observing the same region of sky through different filters that are sensitive to different wavelengths of infrared light. By comparing the brightness of an object in different filters, astronomers can reconstruct its spectrum, the distribution of light across wavelengths. A black hole star should have a very specific spectral signature. It should be bright in the infrared, because that's where the peak emission from a relatively cool, large object would be. But it should also have certain features in its spectrum, corresponding to hydrogen and helium absorption and emission. By comparing the observed spectra to theoretical models, astronomers can determine whether an object is likely to be a black hole star or something else. The problem is that for very distant objects, even JWST's incredible sensitivity is barely enough. These objects are so far away that their light has been traveling for over 13 billion years to reach us. The universe has expanded during that time, stretching the light to longer wavelengths and making the objects appear dimmer. Finding and confirming black hole stars at these distances requires every trick in the observer's playbook. Long exposure times, stacking multiple images, careful calibration, and sophisticated data analysis. In 2024, a team led by Italian astronomer Roberto Maiolino published a paper where they used JWST's spectroscopic capabilities to get an actual spectrum, not just multi-band colors, of one of these candidate black hole stars. The spectrum showed exactly what the theory predicted: a hot continuum with hydrogen and helium lines, and crucially, the width of those lines indicated the material was moving at thousands of kilometers per second, consistent with the gravitational environment near a massive black hole. This kind of detailed spectroscopy is incredibly time-consuming. JWST has a busy schedule with many different teams competing for observation time. But as more data comes in, the case for black hole stars is getting stronger. We're not just finding a few weird objects. We're finding a population of them with properties that statistically match the theoretical predictions. Now let's talk about the future and where this research is heading, because we're at the beginning of this story, not the end. JWST will continue observing the early universe for years to come, and each new deep field image will potentially reveal more black hole star candidates. But JWST isn't the only tool we have. In the 2030s, NASA is planning to launch the Nancy Grace Roman Space Telescope, which will have a field of view 100 times larger than JWST. Roman won't have the same sensitivity to extremely distant objects, but it will be able to survey vast areas of the sky, potentially finding thousands of black hole star candidates. On the ground, new extremely large telescopes are being built. The European Extremely Large Telescope, with a mirror 39 meters across, will be able to take spectra of objects too faint for current ground-based telescopes. This will allow follow-up observations of black hole star candidates found by JWST and Raman, confirming their nature and studying them in detail. There's also an entirely different way we might detect black hole stars: through gravitational waves. The LISA mission, a space-based gravitational wave observatory, planned for launch in the mid-2030s, will be sensitive to the gravitational waves produced by massive black holes. If a black hole star contains a rapidly growing black hole, it should produce a characteristic gravitational wave signal as matter spirals in. Detecting this signal would provide independent confirmation that these objects exist and would let us study the dynamics of the central black hole in ways that electromagnetic observations can't. Imagine a future where we can observe a black hole star simultaneously with JWST's electromagnetic observations and LISA gravitational wave detections. We'd be seeing the same object through two completely different windows, one showing us the stellar envelope, the other revealing the hidden black hole within. This is multi-messenger astronomy at its finest, using every available tool to understand a single phenomenon. But beyond the observations, there's a huge amount of theoretical work still to be done. The models we have for black hole stars are relatively simple. They make assumptions about how matter flows, how magnetic fields behave, and how the object evolves. Real black hole stars are certainly more complicated. They might have magnetic fields that channel material onto the black hole in specific patterns. They might undergo instabilities where parts of the envelope are violently ejected. They might interact with their environment in ways we haven't considered. Sophisticated computer simulations are needed to model these objects in detail. A team at the University of California, Santa Cruz, is working on simulations that follow the evolution of a black hole star from formation to death, tracking millions of particles and solving the equations of magnetohydrodynamics, radiation transport, and general relativity simultaneously. These simulations are pushing the limits of even the world's most powerful supercomputers. But the results are stunning, showing complex flows, turbulent dynamics, and behaviors that simple models miss entirely. One prediction from these simulations is that black hole stars might produce powerful jets, beams of plasma and radiation that shoot out from the poles at nearly the speed of light. This happens with supermassive black holes in galaxy centers, so it makes sense it could happen in black hole stars too. If these jets exist, they would have profound effects on the surrounding environment, heating gas, triggering star formation, and potentially even affecting the formation of the first galaxies. There's also a connection to another mystery of the early universe, reionization. The universe today is filled with ionized hydrogen. The electrons are stripped away from the protons. But in the early universe, after the cosmic microwave background was emitted, there was a period called the Dark Ages, when the universe was filled with neutral hydrogen. Something had to ionize that hydrogen, turning the universe from opaque to transparent. We think it was the first stars and quasars, but the details are unclear. Black hole stars could have played a major role in reionization. Their intense radiation would ionize hydrogen in their vicinity, creating expanding bubbles of ionized gas. As these bubbles overlapped and merged, the entire universe would gradually become ionized. By studying the properties and distribution of black hole stars, we can test whether they produced enough ionizing radiation to drive reionization. I know I've thrown a lot of technical details at you, so let me step back and frame this in a bigger picture. What we're really talking about is how complexity emerges in the universe. The Big Bang gave us a hot, dense, smooth soup of particles. Over 13.8 billion years, that smooth soup became stars, galaxies, planets, and eventually life. How did that happen? What are the key steps in going from simplicity to complexity? Black hole stars are one of those key steps. They took the diffuse gas of the early universe and concentrated it, both in terms of matter and energy. They created the seeds around which galaxies would form. They produced heavy elements that would eventually become planets. And in doing all of this, they shaped the large-scale structure of the universe, determining where galaxies would form and how they would cluster. Without black hole stars, or something like them, the universe would look very different. Galaxies might have formed much later. Supermassive black holes might not exist. The distribution of matter might be much more uniform and boring. In a sense, we owe our existence to these impossible objects that briefly lit up the early cosmos before vanishing into the black holes they created. There's something deeply poetic about that. The most extreme objects in the universe, objects that combine stellar brightness with black hole darkness, objects that shouldn't exist according to our textbooks, are actually fundamental to the cosmic story that leads to us. We're made of stardust, as Carl Sagan famously said, but maybe we're also, in a sense, made of black hole stardust. Now I want to address something that might be bothering you. How certain are we about all of this? Is this settled science or speculation? The honest answer is that we're at an exciting but uncertain stage. The observations from JWST are real and puzzling. The theoretical framework for black hole stars is solid, based on well-understood physics. But the direct connection between the observations and the theory isn't 100% confirmed yet. It's possible that some of the objects we think are black hole stars are actually something else we haven't thought of. It's possible that black hole stars exist, but the specific objects JWST has found aren't them. Science works through this kind of iterative process where observations drive theory. Theory predicts new observations, and gradually we converge on the truth. What gives me confidence that we're on the right track is that multiple independent lines of evidence are pointing in the same direction. The luminosities match. The temperatures match. The number density matches. The lack of viable alternative explanations matches. When everything lines up like this, it's usually a sign that we're onto something real. But let's entertain some alternatives, because good science requires considering all possibilities. One alternative explanation for the bright objects JWST is finding is that they're not black hole stars, but rather dense clusters of normal stars. If you pack enough stars into a small enough volume, from a distance, it could look like a single super bright point source. The problem with this explanation is that such dense clusters should be unstable. The stars would interact gravitationally, flinging each other out of the cluster on relatively short timescales. Another possibility is that we're seeing supermassive stars, stars with hundreds of thousands of solar masses, but no central black hole, at least not yet. These could theoretically exist briefly before collapsing. The challenge is explaining how they remain stable against radiation pressure, which is what the black hole star model solves by having the central black hole provide a gravity well. A more exotic possibility is that we're seeing the signatures of dark matter annihilation in the cores of the first halos without any ordinary matter star at all. If dark matter particles annihilate when they collide, and if the dark matter halos in the early universe were dense enough, you might get enough energy release to create a luminous object. This is speculative, but can't be ruled out yet. The way we'll distinguish between these possibilities is through more detailed observations. Different models make different predictions about the spectra, variability, spatial extent, and evolution of these objects. As JWST continues to observe and as we get data from other telescopes, we'll be able to rule out models that don't fit the data. This is how science advances. We start with a mystery. We propose explanations. We test those explanations against observations. The explanations that survive are probably close to the truth, though we remain humble, because nature has surprised us before and will surely surprise us again. Let me now get more personal and philosophical, because I think it's important to step back from the technical details and think about what this means for us as humans trying to understand our place in the cosmos. When I first learned about black hole stars, my initial reaction was disbelief. Objects that massive shouldn't exist. The physics shouldn't allow it. It felt like someone was telling me that water could flow uphill, or that perpetual motion machines were real. But the more I learned, the more I realized that my disbelief came from a limited perspective. I was thinking about stars based on the stars I know, the stars in the modern universe, the stars I can see in the night sky. I wasn't thinking about the early universe as a fundamentally different environment with different rules and different possibilities. My intuition about what's possible was calibrated to the wrong conditions. This is a profound lesson that applies beyond astrophysics. How often do we dismiss ideas as impossible because they don't fit our current understanding or our limited experience? How often do we miss truth because we're looking through the wrong lens? The universe is under no obligation to match our expectations. It just is what it is, and our job as curious beings is to observe, question, and update our understanding when the evidence demands it. Black hole stars also make me think about the concept of extremes and how the universe seems to love pushing things to their limits. Why have stars that are just massive when you could have stars that are impossibly massive? Why have black holes that grow slowly when you could jumpstart them with seeds that are already millions of solar masses? The universe doesn't settle for modest. When conditions allow, it goes to extremes. There's an aesthetic quality to this, almost like the universe is an artist exploring the full range of what's possible within the constraints of physical law. The same laws that give us delicate, stable yellow stars, like our sun, also give us black hole stars under different conditions. It's all the same physics, just applied in different contexts with wildly different outcomes. This makes me wonder what other extremes might exist that we haven't discovered yet. We found extremes in temperature, density, and mass. What about extremes in quantum effects, in space-time curvature, in the behavior of fields and forces? Every time we push the boundaries of observation, we find new phenomena. There's no reason to think we've reached the end. I also think about the fact that these objects are long gone. The black hole stars JWST is observing don't exist anymore. They lived and died billions of years before our sun was born. We're seeing ancient light from objects that are now just black holes, or perhaps have merged into even larger structures. It's like archaeology, piecing together a history that's written in light that's been traveling across space for longer than the Earth has existed. This should give us a sense of humility about our place in time. We exist in a thin slice of cosmic history, in an era when the universe is relatively old, cool, and stable compared to its chaotic youth. We'll never see a black hole star in real time. We'll never visit one. We can only look back at their fossils, the light they emitted eons ago, and try to reconstruct what they were like. Yet despite this vast gulf in time and space, we can understand them. We can take the light from these ancient objects, pass it through instruments, analyze the data, and figure out what was happening 13 billion light years away and 13 billion years ago. That's extraordinary. It means that the laws of physics are universal and timeless, that the same equations that describe light in a laboratory here on Earth also describe light from the early universe. It also means that intelligence, consciousness, the ability to ask questions and seek answers, is powerful. We're a species of primates on a small planet, evolved recently in cosmic terms, and yet we can understand black hole stars. We can reconstruct cosmic history. We can peer into the universe's infancy and see things that existed long before we did. That's a profound achievement. Now let me bring this to what might be the most important question. So what? Why should you care about black hole stars? You're not an astrophysicist. You're not going to visit one. How does this affect your life? I think there are several answers. First, this is about the origin story of everything, including you. The atoms in your body were forged in stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from stellar processes. And the story of how stars formed, how the universe evolved from the Big Bang to now, is your story too. Black hole stars are part of that story. They helped create the universe you inhabit. Understanding them is understanding where you came from. Second, this is about the power of human curiosity and ingenuity. A few decades ago, black hole stars were just wild speculation. Today, we might be photographing them. That transition from idea to observation happened because humans built incredible instruments, developed sophisticated theories, and refused to accept that some questions were unanswerable. That's inspiring. It shows that hard problems can be solved, that the universe can be understood, that we're not helpless in the face of mystery. Third, this is about perspective. Modern life can feel small sometimes, focused on immediate concerns, daily stresses, interpersonal dramas. Learning about black hole stars jolts you out of that narrow perspective. It reminds you that you're part of something vast and ancient, that the universe is stranger and more wonderful than most people realize, that there are questions worth asking that have nothing to do with money, status, or social dynamics. I genuinely believe that everyone benefits from occasionally stepping back and thinking about their place in the cosmos. It's good for mental health. It's good for maintaining a sense of wonder. It's good for keeping the petty annoyances of life in proportion. When you're stuck in traffic or worried about some minor thing, remember that you're on a planet orbiting a star in a galaxy that might have been seeded by a black hole star 13 billion years ago. Doesn't that make traffic seem a little less important? Fourth, and this might sound strange, but I think there's a moral dimension to understanding the universe. We live in an era of increasing polarization, where people retreat into echo chambers and refuse to engage with ideas that challenge their beliefs. Science, at its best, is the opposite of that. It's about following evidence wherever it leads, changing your mind when the data demands it, and accepting that you might be wrong. Learning about black hole stars, seeing how scientific consensus evolved as new data came in, is a lesson in intellectual humility and flexibility. If we could all approach disagreements the way scientists approach mysteries, with curiosity rather than defensiveness, with a willingness to update our views, with respect for evidence and expertise, I think society would be better off. Black hole stars won't solve political problems, but the mindset that discovers them, that epistemic virtue of questioning and testing and adapting, that's something we need more of. Let me also talk about the technological side of this, because the story of black hole stars is also a story of human technological achievement. JWST is an absurdly sophisticated machine. It has a mirror made of 18 hexagonal segments that had to unfold in space and align to nanometer precision. It's sitting at a point in space 4 times farther from Earth than the Moon, in a delicate gravitational balance. It operates at temperatures just above absolute zero to minimize infrared interference. And it's beaming back data across 1.5 million kilometers using radio waves. Every single aspect of JWST represents thousands of person-years of work, cutting-edge engineering, and scientific expertise. The fact that it works at all is miraculous. The fact that it's revealing new truths about the universe is a testament to what humans can accomplish when we collaborate on ambitious projects. This should make us optimistic about what else we can do. If we can build a telescope that sees black hole stars from the beginning of time, we can surely tackle other hard problems. Climate change, disease, poverty, these are difficult challenges, but they're not as difficult as building JWST or understanding the early universe. What we need is the same combination of long-term thinking, investment in science and technology, international collaboration, and willingness to pursue ambitious goals. Now, as we're approaching the end of this journey together, I want to tie some threads together and leave you with some final thoughts. We've talked about objects that seem impossible, stars with black holes at their cores, masses millions of times that of the sun, existing in the universe's infancy. We've seen how these objects solve critical problems in cosmology, explaining how supermassive black holes formed so quickly, how early galaxies assembled, and how the universe evolved from simplicity to complexity. We've explored the extreme physics of these objects, where general relativity and quantum mechanics both operate at full strength, where time flows differently at different depths, where matter exists in states we can barely imagine. We've seen how modern telescopes are finally able to observe these objects, providing evidence for theoretical ideas that were once just speculation, and we've reflected on what this means, both scientifically and philosophically. The universe is stranger than we imagined. Our understanding is always provisional, always subject to revision as new evidence emerges. And yet, despite our limitations, we can understand the cosmos. We can look back to the beginning of time and reconstruct what happened. If there's one message I want you to take away, it's this. You live in a universe that is endlessly fascinating, full of wonders and mysteries that we're only beginning to uncover. Black hole stars are just one example. There are countless others. And the process of discovery continues. Every year, new telescopes come online, new data pours in, and our picture of the cosmos becomes richer and stranger. You're part of that story. Even if you're not a scientist, even if you never do research or publish papers, you're part of the community of curious minds that cares about these questions. By watching videos like this, by thinking about these ideas, by sharing your sense of wonder with others, you're participating in humanity's grand project of understanding our place in the universe. The black hole stars that JWST has found don't exist anymore. They burned bright for a cosmological instant and then collapsed into the black holes that would shape the future universe. But their light is still traveling, still reaching us, still telling us their story. And we're here, 13 billion years later, smart enough and curious enough to listen. That light has been traveling longer than the Earth has existed. It's crossed a universe that expanded from a size smaller than an atom to its current vastness. It's survived for eons, and now it's hitting JWST's golden mirror and being converted into data, into images, into knowledge. And that knowledge is changing how we see the universe and our place in it. When you go outside tonight and look up at the stars, remember that you're looking at a universe that was shaped by objects you can't see, objects that existed before almost anything else, objects so extreme that they combine stellar brightness with black hole darkness. Remember that the supermassive black holes at the centers of galaxies, including our own Milky Way, might have started as black hole stars in the cosmic dawn. Remember that the universe is not static. It evolves. It had a beginning, and it will have an end, though that end is so far in the future that we can barely conceive of it. We exist in a particular epoch, neither at the beginning nor the end, but at a time when stars still shine, when galaxies still form, when complexity is still increasing. And remember that you are made of atoms forged in stars, organized by billions of years of evolution into a pattern capable of thought, of wonder, of asking questions about black hole stars and the origin of the cosmos. You are, in a very real sense, the universe becoming aware of itself. When you think about black hole stars, you are the cosmos contemplating its own history. That's not just a poetic sentiment. It's literally true. The atoms in your brain right now were scattered across space billions of years ago. They've been through stellar cores, supernova explosions, interstellar clouds, and the formation of the solar system. They've assembled into you, temporarily, and they're processing information about their own distant past. The universe is thinking about itself through you. I find that deeply meaningful. It suggests that consciousness and intelligence aren't accidents or anomalies. They're what the universe does when it gets complex enough. Stars create heavy elements. Planets form. Life emerges. Intelligence develops. And then that intelligence looks back and tries to understand the stars that made it possible. It's a beautiful cycle. Black hole stars played a role in that cycle. By creating massive black holes quickly, they shaped how galaxies formed. By producing heavy elements, they seeded the universe with the ingredients for planets and life. By existing at all, they showed that the universe in its youth was capable of extremes we're only now beginning to appreciate. So the next time someone asks you what's the point of studying distant objects that existed billions of years ago, you can tell them it's about understanding where we came from, how the universe works, and what's possible within the laws of nature. It's about satisfying the curiosity that makes us human. And it's about participating in something larger than ourselves, a multi-generational quest to understand the cosmos. The discovery of black hole stars, if confirmed, will be remembered as one of the great revelations of 21st century astronomy. Alongside the detection of gravitational waves, the imaging of black hole shadows, and the discovery of thousands of exoplanets. It shows that the universe still has surprises for us, that we haven't figured everything out, and that the next generation of telescopes and scientists will undoubtedly find things that seem just as impossible to us as black hole stars seemed a few years ago. And who knows? Maybe some of you watching this will be part of that next generation. Maybe you'll be the one to confirm the existence of black hole stars definitively. Maybe you'll discover the next impossible object. Maybe you'll be the one to develop the theory that explains something currently mysterious. The future is open, and there's so much more to discover. Before I close, I want to acknowledge something. I've presented a lot of this as if the black hole star interpretation is definitely correct. And I should be clear, we're not 100% certain yet. The scientific process is ongoing. More observations are needed. Alternative explanations need to be fully explored. It's possible that in a few years, we'll have a different understanding of what JWST found. But that's okay. That's how science works. We make our best interpretation of the available evidence, we test it, and we adjust as new data comes in. The excitement isn't just in being right. It's in the process of figuring things out, in the back and forth between theory and observation, in the gradual convergence toward truth. What I'm confident about is that whatever JWST found, it's something important and interesting. Whether it's black hole stars, specifically, or some other exotic phenomenon, we're learning about the early universe in ways that weren't possible before. We're seeing farther back in time, with more clarity than any previous generation of humans. That's worth celebrating regardless of how the details shake out. Thank you for sticking with me on this journey through one of the most exciting frontiers in modern astronomy. If your mind is blown, if you're seeing the universe differently now than you did 3 hours ago, then I've done my job. Never stop asking questions. Never stop wondering. And never stop looking up at the sky with awe and curiosity. The universe is vast, ancient, and full of wonders. Black hole stars are just one chapter in an endless story. And that story continues, with or without us. But it's so much richer when we're here to witness it, to understand it, and to share that understanding with each other. Keep exploring, keep learning. And remember, you're made of star stuff, contemplating star stuff, in a universe that somehow gave rise to both black hole stars and to you. That's pretty amazing when you think about it. Clear skies, everyone.